I'm starting the recording. Yeah, this is a seminar for the seminar in Bangalore, India, and it's about time frequency analysis and suitable function spaces. The original goal and the abstract was a little bit too ambitious. I was planning to talk about a variety of function spaces, including amalgam spaces and modulation spaces, which are really useful in the context of time frequency analysis, but also for classical harmonic analysis. But at the end, I decided to rather give an alternative perspective. I must say I was just finishing a course. Maybe I show meanwhile some books in the area that you can take a look. So I have given a course at ETH Zurich, which was a course for engineers and mathematicians and physicists, and an advanced course which I would call a convenient approach to distribution theory. So normally distribution theory is coming after Lebesgue integration theory, topological vector spaces, functional analysis, and so on. But I think nowadays we should start from linear algebra through functional analysis and rebuild Fourier analysis from scratch using those function spaces which are relevant for time frequency analysis. And so the emphasis of this talk will be on the questions that arise in this way. So I will tell you a lot about a triple of spaces which I call the Banach Gelfand triple, and it consists of the space S0, which I was calling the Segal algebra, a special Segal algebra. It's not the Segal algebra, it's a Segal algebra, but it is distinguished within the family of all these Segal algebras as introduced by Hans Reiter, my advisor, because it's the minimal one with the extra property of being translation invariant and Fourier invariant. So S0 is a very nice, decent space of continuous Riemann integrable functions. Its dual space is, of course, rather large, but still much smaller than the space of tempered distributions. So that's why I'm using, meanwhile, the terminology. It's the space of mild distributions. And in the middle, between the two spaces, you have the classical Hilbert space, the L2 space. So sometimes people talk about a rigid Hilbert space because you have L2 decorated with some smaller and some bigger space. And people in partial differential equations certainly think of Sobolev spaces which behave in a similar way. But the interesting thing is here, S0 is a Banach space, it's not a Hilbert space anymore, and still you can use it in many places as a good replacement and improvement even of the Schwartz theorem. These spaces are special cases of the so-called modulation spaces, and in that list they would appear as M1, M2, and M infinity. But I will not go into this aspect here. I rather use this symbolic representation, whereas people very often say, when you do Fourier analysis, you have Plancher's theorem, you should work with L2. Well, this is absolutely right. But we know already that even for the definition of the forward and the inverse Fourier transform, we're not able to use Lebesgue integration theory because L2 functions may not be Lebesgue integrable. Just think of the Fourier transform of the rectangular function, the sinc function, which is not L1. And of course, what you do is you approximate it and you are taking limits of approximations, and this way you prove Plancher's theorem. I use very often when I teach this course or this material, the analogy to the number system. So replace the interior by the rational numbers, the yellow area by the real numbers, and the outer part by the complex numbers. Then the yellow area would be where we do our formal computations. We would write pi multiplied with 1 over pi is 1. But 1 over pi is not just like a rational 3 or 4, but it's a real number which is well defined. And I think that many times when engineers or physicists write integrals, they're meant in the sense of the bigger world. The outer world is where we can do things that we cannot do inside the Hilbert space, especially over the Euclidean space. So even on the real line, a function which is bounded may not have a Fourier transform, of course, in the sense of Plancherel, but as a mild distribution, it has a Fourier transform. So I will give you a motivation how we can approximate these things. You can do the reading here later on, and I don't go into detail. Among others, just to give you a glimpse on the benefit of the outer layer, I would tell you that the usual integral that engineers would write and say, if you add up all the frequencies, then you get the Dirac delta. They would say the Dirac delta function. And this is just another way to say, well, whenever you write an integral of this form with something here, like f hat, you're recovering the function. So this is a symbolic representation of the inverse Fourier transform. And of course, the inverse Fourier transform of constant one is supposed to be the Dirac measure, because in the other direction, it's quite easy, of course, to observe that the forward Fourier transform of the Dirac delta is just the pure frequency. So this is one of the ways where you see a symbolic manipulation, which is quite obscure in the engineering or physics literature, can be turned into something concrete, and you don't have to use Schwartz theory. Now, another thing that I would like to mention is that we can use this whole approach to work in the spirit of a good numerical analyst. So the integral for a numerical analysis is something that you are not realizing by taking Riemannian sums, but by trying to discretize in an appropriate way and taking limits in an efficient way, maybe not for the full class of the integral, but for a restricted class. So take a trapezoidal rule. It's much faster for an approximation of the numerical integral compared to Riemannian sums. And somehow this spirit is missing in the world of harmonic analysis. We have the engineers playing with symbols and having their applications. We have the mathematicians who are pedantic about the convergence of integrals, but they are talking not well enough to each other. So let me just mention a citation that I learned from Yves Meyer. At the time when wavelets were just popping up, I was visiting him and he was telling me, well, you know, function spaces are only good for the description of operators. Just to play around with function spaces for themselves is not meaningful. So I was a little bit objecting to this statement, because I really think that he was, or the people developing wavelet theory have been lucky in the following sense. They were first studying Calderon-Sigmund operators. They were finding that the classical function spaces, Biesov-Triboli, Sorkin, Sobolev spaces, and so on, are appropriate for it. And then they were discovering that they can be understood better using wavelet expansions. Now, my story is a little bit different. I was playing around, developing modulation spaces, and it took a while until one understood which operators can be well described with Gabor expansions or wavelets. So somehow, if you are doing studies broad enough with a perspective on the applications, and here you have some references to these papers, then there is a chance that you can do something useful. But you also see the technical report about these spaces appeared in '83, while they were only published after a conference organized by Professor Rada in Chennai in 2003. But since then, there are hundreds of publications in this area. So yes, modulation spaces are useful, and they are not so popular yet, but they can be used in many areas, including classical ideas. So it's not restricted to the world of time frequency or Gabor analysis. Now, meanwhile, I have a lot of experience by talking to engineers. We had joint projects with the people from communication theory, and also with presenting the material to engineering students, or to talk to a wider public. What is the role of mathematics in the modern technological world? So this picture is just showing a glimpse on the WAV player, that media player that people have very often on their computer. It's a spectrum of a sound at a certain moment. And this means that at a certain frequency here, you have a strong contribution. So you would see this going up and down over time. And so here you would have the frequency axis from left to right, and time would be passing through by showing the different pictures. So this is something that people can use. And what I want to emphasize is you can look at this, you can understand these problems without knowing that this is something that you can compute. You would not want to know whether this recorded sound signal has a value, the correct value almost everywhere and so on. So I think that's what you can take from this picture. I always recall to you that you should use the Gaborator, and the Gaborator allows to put up your own WAV file, and you see these pictures. Okay, so the Gaborator you can do yourself. We have seen some piece of Mozart. I was doing it in a live presentation. Depending on the quality of your microphone, you can see here the frequency and the time. So this is the intuitive picture of a spectrogram. You can say it's a graphical score, but computed using discrete data from a sound signal. So this is really from the recording through a microphone. Now, I will jump ahead and tell you that I have essentially done 3 survey papers over the years, which could help you to understand the wider scenario. So Gabor analysis is something that you can do over any locally compact abelian group. So normally you would start to say, we have a group, which is a locally compact group. The group operation is abelian, and you have pure frequencies, or so-called characters. And then you can define time frequency shifts, which means delay operators or shift operators. Combined with the Fourier transform, you would do shift operators on the Fourier transform side, also called modulation operators. And you can do it on any finite group. So what is the advantage of doing it in a finite group? You're not bothering about infinite integrals, convergence problems, and so on. So in this paper with Werner Kotzek and Franz Luev, I was writing down all the details, which is the purely algebraic aspect of the theory. Another aspect is that in Gabor analysis, you have to deal with so-called frames, and usually people say they are generalization of orthonormal systems, but I would say they're just easy generalization or natural generalizations of the idea of a generating system. Everybody knows what it means that 5 vectors in R3 are generating the whole R3. And normally I'm showing all my hand with 5 fingers in a general position to demonstrate what a frame of redundancy 5/3 in R3 could be. So you can do all these things from the point of view of linear algebra and redundant systems instead of basis. And then we come to the functional analysis, and it's not good and not helpful anymore to stay, and that's the topic of my talk here, to stay with ordinary spaces like LP spaces, because they're not suitable to describe those questions that arise naturally in Gabor or time frequency analysis. So in the study of these spectrograms, you're not able to describe the objects properly, you're not able to describe boundedness of operators. And this is why we are, I will talk mostly about this Banach Gelfand triple, again, consisting of the Segal algebra as 0, sometimes called Feichtinger algebra, L2 as a Hilbert space in the middle, and as 0 prime, the space of mild distributions as the big space. I also have inserted a couple of master theses which have been written under my guidance in Vienna, mostly because you can download them from our site if you are interested, and they were summarizing material I had at the time in a nice way. They're all written in English so that you can understand and read them if you want. There are also some other recent papers where I try to popularize these ideas from different angles, but this is something I don't have to show to you. And also the foundational papers, some of them already appearing in our book from '98, are showing what a Gabor multiplier is, what is the role of these test functions and so on, but I will do some of these things earlier on. So in order to start from the linear algebra side, that's one of the possibilities. So instead of saying we all know L2 and we are defining S0 as a subspace of L2, let me do the linear algebra and I will switch now to we'll switch to the presentation of in MATLAB sense. Now, before doing this, let me just recall that in linear algebra, we are learning, or we're teaching our students, that the linear mapping between two finite dimensional spaces, so I'm using the standard conventions, a linear mapping from Cn to Cm can be realized by matrix multiplication. And usually matrix multiplication is understood as something moving the vector x into the new vector a of a multiplied with x. But we should also read it as a linear combination machine. The vector x decides how many, the coefficient of the column vector of the matrix A that is used in order to do a linear combination. So clearly an m by n matrix has n columns, therefore you can only apply it to a vector, a column vector of length n, and you're getting linear combinations. But with every matrix, okay, and then special cases, of course, if you put a unit vector, then you're getting 1 times the column, so you're getting this identification. Now, a matrix can be also put in transpose format, or more correctly for the complex field, into a complex conjugate, and then multiplying now a vector of length m with the transpose conjugate, you're getting the scalar products. So matrices have these two properties that you can multiply to do linear combinations, or that you can multiply with the transpose conjugate in order to get the coefficients. Clearly, the double prime is the original one, and we are talking about the column space of the matrix and the column space of A prime. And if we're sloppy, a little bit sloppy, or if we are in the real world, we would just say this is the row space of A. But the difficulty is you cannot apply by left matrix multiplication a matrix to a row vector. That's why it's really better to think of, when I hear the word row space, I think of the column space of A transpose. Now, there is a simple observation saying that if you have such a linear operator as you have it in linear algebra, and you restrict it to the row space, and now really it's the column space of A prime, then more or less you're removing the zero space of your linear mapping. Because the null space of a linear mapping is the null space of the linear mapping induced by A prime is exactly no, I'm now confused. Sorry. So I should go back. The column space is this target space. That's all the possible linear combinations that you get. The orthogonal complement, if you rewrite it in 1 or 2 lines, is just the null space of the mapping A prime. Okay, so if you change the roles, then you find that the orthogonal complement of the null space of A is just the row space of the matrix. This means if you restrict your T, you have thrown away the orthogonal complement of the row space or the null space, so there is no null space. So you're restricting your mapping to the row space, you're getting an injective mapping, and of course you're not losing anything in the target space, you get an isomorphism. So we all know that the row rank is the same as the column rank of a matrix. So you have now on the within Cn you have the row space, within Cm you have the column space, and therefore you're having four spaces, these two spaces, and their orthogonal complements. Now I would like to recall the concept of a pseudo-inverse of a matrix, which you can do later on in the Hilbert space setting, and that's if you have a closed range, it's just inverting the injective mapping from the range back to the unique domain, which is the row space. And usually it comes up in linear algebra in this way, or numerical linear algebra, as the problem where you solve the minimal norm least square problem, and you're asking, can I solve ax equal b for a given b? Now, if b does not belong to the column space of the matrix, you have to project it. You're doing a change, but you get this optimal solution, or it's an optimal replacement, by taking the pseudo-inverse. It's, okay, it should be b, of course. X is the pseudo-inverse of a applied to b, and if you take that x, then you get the optimal approximation. But also because it's in the row space, there is no unnecessary part of the null space of the synthesis mapping. That means you're getting the minimal norm least square solution. So roughly speaking, if you do the singular value decomposition of a matrix A, a rectangular matrix of rank R, then you're getting the basis U of the column space, basis of the row space, and you can represent the matrix either by factorizing it or by writing it in the form of scalar products. So it's a diagonalization, of course, of matrices. Now, this is something that you can do in MATLAB, and I'm not talking too much about this. Just I want to tell you, if you're in the good situation that your column vectors are spanning everything, then of course every vector can be represented, but it can be represented in many ways. And then the minimal norm property comes in. So I would like to represent the vectors among all the possible representations by those with minimal norm in the Euclidean sense. And so in this sense, you can do linear algebra in the terminology of frames by saying, well, it's just that the pseudo-inverse allows you to take to get the dual frame. I call it A tilde, to be the pseudo-inverse of A prime, which is the same as the pseudo-inverse of A, and then transpose conjugate. Now, the advantage of this writing here is that A tilde has the same number of vectors in the same space. So for every frame, every generating system, you get an optimal dual system. There are many such things, but the one delivering the minimal norm coefficients is the pseudo-inverse, the dual frame. And if you're transposing the whole thing, then you're getting linear independent things. And maybe I show you only my old favorite formula, which is a formula easily derived from the properties of the singular value decomposition, that the pseudo-inverse can be written in both ways. And if you're lucky, and this means if your matrix is of maximal rank, that you can choose this or the other one to be an invertible matrix. So if you have linear independent vectors, then you would invert the Gram matrix, which is this guy here. Or if you have a generating system, which is our case, then you would do this with the frame operator. So the frame operator says, I'm taking first the coefficients, and then I'm taking a synthesis. So let me see, maybe I should mention, I like to mention the Löfdin orthogonalization, because this is something that is not so well known in general. So everybody knows the Gram-Schmidt orthonormalization. You take a linear independent system and you start by putting labels on the vectors, and the first is unchanged up to normalization. The second, the third, and so on are always have to give up everything that is covered by the earlier one. But if you want to have a more symmetric version, which is permutation invariant, then using the gram matrix to the power -1/2 is the good way. And so for the case of generating system, if you're having these 5 vectors in R3, you can modify them with help of this frame operator S and take S to the -1/2 and get a system which is redundant but still has something that, let's look at like if it was an orthonormal system. Note, it's not orthogonal, it's not normalized, it can be shown to be an orthogonal projection of a larger, higher dimensional orthonormal system onto a lower dimensional space. But this kind of system is really what we want to use for Gabor analysis. So now I'm really jumping to a MATLAB live file, which means I'm probably just showing you the file without running anything particular. Let me see. Yeah. I hope you can see now. No, I'm not sure. I have too many windows open. Yeah, you should be able to see now the MATLAB window. So please let me know if there's a problem. And I don't go through all these things. You can read this later. And just tell you what my linear algebra approach would be to do this. So this is actually material I'm preparing for a seminar talk of one of our students in Vienna for the coming weeks or so. So if we do the finite group, the cyclic group of order n equals 480, and we're doing time shifts by 20 and frequency shifts by 16, two divisors of the signal lengths, with redundancy 1.5 or 50% if you want, we have 720 positions of our time. And we start with the Gaussian, which is a discrete Gaussian, which looks like this. You see it on the right-hand side. We use the matrix describing the discrete Fourier transform. And this really means apply the FFT command to the collection of unit vectors, which is the unit matrix. And then we can look at the time frequency shifted version. Rod mod is cyclic rotation of RG. So you see it's a little bit offset from the 0. And this is the Fourier transform. So you know the rule that if you shift a function, its Fourier transform, which is a Gauss function again, is multiplied with the thing, with a pure frequency. It has a certain number of oscillation. And on the other hand, if you're the second one is you're multiplying with a pure frequency. So with column number 11 of the Fourier matrix, I could say, then it's a shift on the Fourier transform side. So transposing a piece of music is multiplying it with a pure frequency. Now, the STFT of a random signal looks like this. So the command is just, I'm computing for every time shift a Fourier transform. So at the points here are going from left to right. I multiply my random signal with the Gauss function G, shifted by the number of pixels which are left and right. And in the vertical, I plot the short time the Fourier transform of this localized version. So whereas classical theory says I get a Fourier transform by making the period bigger and bigger and getting infinite resolution, I'm here just doing this, that I'm localizing the function. And I wouldn't take the whole symphony, I would take local pieces, and I would take a Fourier transform of the local pieces. And you have seen the pictures so that they are really meaningful. So this is kind of the MATLAB version of these real-world spectrograms. And if my lattice is exactly the points marked in black, I would ask the question, can I recover this continuous short-time Fourier this signal, this random signal, or arbitrary signals from a sampled short-time Fourier transform. Recall that by computing the full short-time Fourier transform, I would do n squared samples from n samples of the sound signal. So I would have a redundancy, which in our case would be close to 500, incredibly large. And you see also there is a kind of smoothness, but it's not band limitedness in the ordinary sense. You could not take this picture and say, I do interpolation first and then recover. That would not work. It's highly oscillatory. We're seeing only real valued here, absolute values of the short-term Fourier transform here. Now, these commands are essentially telling you that I can recover I can represent the short-time Fourier transform sampled at the black points by doing scalar products with my family of Gabor points. So what I'm doing here is the following. Look at any of those points. You see that we have 720 points. Each point has an offset from the 0 to the right, which is maybe 1 to 3 times a 60 pixels shift in the cyclic way. And then a multiplier with the pure frequency might be this one here. And then the value of the short-time Fourier transform here is one of these values of a sampled short-time Fourier transform. And here it's just, this demonstrates that really sampling the full continuous at this position is done efficiently by this special command. But then the values that I get by taking this Gabor family, and I could do also this here, I could recall that the Gabor family is just a family of 720 elements. Okay, so I have not, I should rerun it. I don't want to. So you should, maybe I'm doing this, insert a section break, and then it should work. Okay. Okay, so I'm sorry, I shouldn't start playing around. Just to show that it's really a equal 20, b equal 16. Maybe if it works, it's fine. If not, I will stop doing this. The point is, yeah, here we see that this system of Gauss function is a collection of 720 functions, and I put them as row vectors because it's more natural for me to look at a collection of signals. And in each of these, you have a Gauss function shifted by a certain amount, modulated by a certain amount. And this is just telling you, and then a basic observation, that either taking the scalar products, so taking scalar products with all those 720 Gauss atoms, is the same as computing the sampled short-time Fourier transform. Now, the rest, I don't go too much into the details, but the rest should tell you that if you're taking the minimal norm solution by computing the dual family a priori, and then you're taking the first row and you're rebuilding from that first row a Gabor system, so you're moving them around in the same way with time shift frequency shifts, then the result tells you that this is a Gabor family. So the message is, if you're taking any lattice in the time frequency plane and a discrete subgroup, and if you get a frame, so a generating system in the finite dimensional case, then the dual system will be also a Gabor system with respect to some dual thing. Now, the command which is coming later is just demonstrating that we have different efficient codes like Peter Prince dual window code or Gabor dual by Hans Feichtinger for a general lattice, and all these things allow you to compute this thing very efficiently, which means, and then I'm just going to this here, that you can recover the original signal, which was a random signal, from the STFT by synthesizing with these coefficients, so 720 coefficients, with the dual window. So that would be the question of, can I recover the signal from a sampled spectrogram? We have been interested in another question, can we rebuild from a Gabor system, so from a G with along the lattice A and B? And the answer is yes, we can do it by choosing the coefficients to be the samples of the short-time Fourier transform. So I would say it's X applying under the G dual prime, so taking scalar products with the dual family, but it's also the same as saying, well, we take just an easy short-time Fourier transform, but with respect to the dual window. And the same lattice A and B, and that gives us the right coefficients. Here you see all these things. The comp norm routine just says if you have two vectors, they could be a row or column vectors or different formats of equal total lengths. And then if they are not equal lengths, you would not have an 1 here, but otherwise you see it's all numerical precision that you have here. Maybe I just show you at the end the tight case. So the tight case would be, instead of taking the inverse frame operator applied to the G, you can take the inverse frame operator to the -1/2, and you're getting this nice object. So you see it's a deformed Gaussian, it has some side lobe, it's a little bit of negative values, but it has this very good property that if you're doing analysis and synthesis with this tight window, so you see GT is the tight Gabor family. It's a family of 720 vectors, which are used such that if you do, I'm doing right matrix multiplication, first scalar products, then synthesis, you're getting the identity operator. So this is also directly represented. You're saying, if I do Gabor synthesis with this tight Gabor atom, which you have seen here on the right, then you can use the coefficients in the same way. So this is the good way. You see the redundancy was reduced from the 480 to 1.5. So we are much better, like by a factor of more than 100 better in terms of redundancy. And later on, which I will not go through, I can say I can multiply the Gabor coefficients with some numbers. And what this would show you here is that the difference between I'm not sure. Yeah, maybe it's not worthwhile. The difference between the Gabor multiplier, which is done in a continuous way, so you would do what people call a short-time Fourier transform multiplier. So it's really, or the tight Gabor, which is you're taking Gabor coefficients by taking scalar products, then you multiply the values of your weight function on phase space, and then you're doing synthesis, that this difference is quite small. So I would say this is more than enough for going to the continuous world back. So I will resume my presentation. Let me see. Sorry. Here it should be. Yeah, so now the quick summary, you can read this quietly later on. We have formally, if we are in a continuous world, a shift operator, a modulation operator, and the short-time Fourier transform is obtained by combining this first time shift and frequency shift to a time frequency shift. So if lambda is a point in the complex plane, you with coordinates t and omega, or t and s sometimes, you would say the time frequency shift is applied. So you're moving your sensor through the phase space and you're doing the correlation. So it's like a continuous wavelet transform, but now it's a continuous localized Fourier transform, a short time Fourier transform. I don't have to show this picture, but now I have to explain to you quickly what a zero is. So in this context, it's just the set of all the L2 functions for which such a short-term Fourier transform is well defined. Maybe I say at the moment, take here G a normalized Gauss function, so a Gauss function normalized with L2 norm equal to 2. And then you are assuming integrability of this short-term Fourier transform. So this integrability implies that this function f itself has to be a continuous function inside the Fourier algebra actually, but also inside of the continuous functions. And so it's continuous Riemann integrable, absolutely Riemann integrable functions. Now, the good thing is that this condition is invariant with respect to time frequency shifts. Well, it's quite clear because if you play the same piece of music a little bit later at a different tune, you see the same landscape, but just shifted, so the integral is not changing. And it's invariant in the Fourier transform. This is based on the observation that you can that the Gauss function is Fourier invariant, and that the Fourier transform is realized as a rotation by 90 degrees in the phase space picture. Now, of course, you can ask, can I replace the Gauss function by another function? And the answer is yes, you can take any function as zero, but then you have to know that every function with compact support with an integrable Fourier transform is okay. So triangular functions, trapezoidal functions, any piecewise linear function is in L1 is fine, or any Schwartz function is fine. So it's a big reservoir, and actually all the classical spaces are in it. I like to show this demo. So S0 is inside of all the LP spaces. You have here a symbol in the old way, and now I'm using this for L1 and the rotated version for FL1. The round object would be L2. The yellow object would be the domain for the Fourier inversion formula, and that gives you an orientation about this. Now, the triple has actually a lot of structure. So it's actually a category, and if you want to show mappings, you have to show that the inner space is mapped to the inner space, the Hilbert space to the inner space, most of the cases unitary. The outer space is norm to norm, and weak star to weak star continuous. So this is really a setting that you can have, but it's much easier to say that if you have these objects, then you have 3 layers, but you have 4 forms of continuity. Now, I would like to only mention that such a Banach Gelfand triple and Banach Gelfand triple isomorphism already exists in the literature for a very long time. You have the classical Fourier series expansion of L2 functions on the torus, which maps to L2. And then you can ask, what are those which have an absolutely convergent Fourier series, the A of t of Wiener? And it's just corresponding to L1. So if you expand this by transposition or by distribution theory, you're getting the space of pseudo measures, which are just making this whole thing to a Banach Gelfand triple and this to a Banach Gelfand triple. And we also know that L1 is not norm dense in L infinity, but it's weak star dense, which just means coordinate-wise convergence. And exactly this happens so here. So the Fourier transform in the distributional sense is just an extension of this as a Banach Gelfand triple isomorphism. But when you go to the continuous non-compact case, so A of R is well defined as the Fourier algebra, but it doesn't have the same properties as you find with S0. So as a demonstration, I can give you a statement that for me, the Fourier transform is an isomorphism in the sense of Banach Gelfand triples with the Banach Gelfand triple from with S0, L2, and S0 prime. Now, what does it mean? At the S0 level, it's more general than Schwartz, but of course it's less general than Lebesgue integrability. But you can prove this isomorphism property. That's something I did only in the last few years, just using Riemann integrals. Then you can use this isometric property in the L2 sense to prove Plancherel in the same way. But then you can also take duality, so you're using this standard formula, now with Riemann integrals, to extend it to the dual space. So the standard formula, which you know from temporal distribution, but you can do it independently, is if I have sigma in S0 prime, sigma hat of f is just sigma of f hat. And this makes the extended Fourier transform a weak star to weak star continuous thing. And because all these spaces are weak star dense in S0 prime, it's the unique extension. So I can claim that the Fourier transform is a mapping which is defining a Banach Gelfand triple isomorphism in this setting. But in this big space, you also have something like Dirac measures or pure frequencies. And of course, a musician would say, I have analyzed the sound and I have heard a pure frequency, and you would say, yes, the Fourier transform of a pure frequency should be a delta. And in this setting, this property is coming in a unique way. Now, the short-time Fourier transform allows to connect with time frequency analysis. So if we are using something close to Plancherel or Plancherel theorem, then we can prove that the short-time Fourier transform, so the mapping from f to the short-time Fourier transform with respect to a window G, which we assume to be normalized in the L2 sense, is an isometric mapping from L2 of lower-them at the signal space to L2 of phase space. So you should think of R2D as RD cross Fourier domain of RD. Now, this allows to, by abstract arguments, if you have an isometric embedding of a small Hilbert space into a big space, then the adjoint is just the inverse on the range. So you can define back from this to this a VG star, and you're getting the formula that f is recovered from this, but a VG star, if you think of matrix multiplication, is doing linear combinations. Now we're doing a finite or infinite continuous or superposition. Actually, the d lambda is missing here. So we are summing up over all these things. The coefficients are the values of the short-term Fourier transform. These are the building blocks of our Gabor matrix if we would do it in a finite discrete setting. And this is the reconstruction formula. In fact, it can be shown that VG is mapping S0 of RD to S0 of R2D. That means the adjoint mapping is mapping back S0 prime of 2D into S0 prime here. So you can even ask what is happening if I instead of taking a short-term Fourier transform, I put a Dirac, a delta set. And by no surprise, of course, if you integrate the vector valued function pi lambda g against delta set of lambda, you would get exactly pi set of g. So this inverse mapping is exactly mapping a Dirac to a building block in this Gabor expansion. Now, the natural question is, if we are doing this in the most natural setting, traditional setting of the real line, and your time frequency lattice is using a time gap A and a frequency gap B, is this mapping continuous from L2 to the natural sequence space little L2? And the answer is no, unfortunately not. Not every L2 function. Also, it gives you a continuous function which is square summable. The samples may destroy this property. So in the terminology of modern frame theory, you would say this Gabor family may not be a Bessel family, so the whole discussion whether it's a Gabor frame is not reasonable. But and at the same, you cannot say that it's adjoint, which is the synthesis mapping, is also should be bounded from the sequence space on the lattice to the Hilbert space back. So both of them might not be bounded. So what is the way out? Well, use S0 when you want to restrict yourself, not Schwartz, that would be far too much. So I'm stating two little things. One is if you're using a window G for analysis, and of course the same for synthesis, or a different one also in the same space for synthesis, you would move from the signal space L2 to the sequence space L2 and back. So the frame operator, which is a composition of the two now, here you see it explicitly, the frame operator of the Gabor atom G with respect to the lambda is written this way, would be a bounded operator for any G in S0, and any lattice in particular. So you can start discussing the question, when is this frame operator invertible, which is equivalent to this representation property or so. The other way, which I have no time to discuss in great detail, would be to say, well, no, I find it natural that you are getting building blocks. I mean, your window and your signal should, the F and the G should be both in L2. But then the mapping properties have to be described in different way. You're not getting a mapping anymore from L2 to L2, or even from S0 to L2, but you have to say the following. I have to restrict the domain of the frame operator. So once more, the frame operator is this operator. It's difficult in the sense it's unbounded on L2, perhaps, but if you restrict it to S0, it maps S0 into L2. This is just flipping the roles of window and signal. And then if you start from L2 and you're doing synthesis with a window in S0, you're ending up in S0 prime. So the frame operator is an operator which definitely is well defined as an operator from S0 to S0 prime. But it also commutes with all the original time frequency shifts from your lattices. And that's in turn quite important in order to analyze these operators. In matrix theory, in linear algebra, I could explain quickly to you that every n by n matrix is a superposition of n squared time frequency shifts. So these time frequency shifts form an orthonormal basis of the Euclidean space of all n times n matrices endowed with the Frobenius norms, which is nothing else but taking the matrices as if they were pixel images of with n squared pixels or so. So this is called a spreading representation. Now, if you would have a spreading operator who is mapping Schwartz space into a temporal distribution, then you could show that the spreading representation is concentrated on a lattice, which would imply that it is a sum of Dirac measures, but also of derivatives of Diracs. But here we are able to show that you have a continuous version of this. I don't have time to go into the kernel theorem, spreading representation, Kornierberg symbol, but I would like to mention that this setting is good enough to show that such an operator has a spreading representation, or if you want a Kornierberg symbol, or a kernel in the sense of Schwartz kernel theorem, which is in S0 prime of R2D, and because the commutation relation is valid, it must be concentrated on a discrete lattice, which is known to be the adjoint lattice, but you could also say it's the commutator lattice. It's all the sets of points in the phase space which commute with the pi lambda, or the pi lambda 0 commutes with the pi lambda that you have here. So this is another situation where S0 prime can be used to discuss problems coming up in time frequency analysis. When we were doing this theory, we were also thinking of implementing and approximating the continuous thing by the discrete one, and I just want to show you a glimpse of this world. The first one is, well, if you're giving me two irrational lattices and I want to do an approximation with a finite example, then I have to do a rational approximation. And so the question was very natural, well, what happens with my dual windows if I change the window or if I change the lattices? Now, changing the window in the S0 sense is harmless because it means changing the frame operator and therefore the inverse frame operator. Changing the lattice is more delicate because In this way, it's not anymore an operator continuity, but you can say that in the strong operator topology, so you're applying frame operators with slightly different lattices to any element of S0, and you find you have convergence. And it turns out with some effort, as in our paper in the transactions, you can show that the dual window that you have to do for a reconstruction will be convergent, and it will be convergent in the sense of S0, which is very important, because that will mean that if you use a computed approximate dual window in the formula, then the operator norm of the reconstruction will be harmless. So essentially, I would say you might be interested in the L2 setting, but for an irrational lattice, then I would compute everything with a finite dimensional approximation of a rational approximation. I would use this as a replacement, and I could guarantee that the operator thus working in the continuous domain is away from the original one only by a certain percentage, let's say a 3% error. Final part, just something that I'm doing in much detail in the course at ETH, is the Poisson formula has a big range, and the biggest I know is S0. So it's this formula which in the distributional setting is just equivalent to say that the Dirac comp, the sum of the Dirac measures, is invariant under the Fourier transform. But you can do it for more general things. We have a Shannon sampling theorem with a little bit of oversampling. So going from the signal, which is a band-limited signal, to the sampled signal, which has a spectrogram, which is a repeated one, is, well, here done with MATLAB, but we can prove everything to be correct. If you choose such a window, the red guy is supposed to be, or can be, because it's smooth enough, will be in S0, and therefore the reconstruction that we get looks like this. So this is an illustration in MATLAB. Whereas the abstract formula looks like this, and you're getting a recovery of the function f, which has a compactly supported Fourier transform from the values, which is not only true in the Hilbert space, but true in a much better sense. So it has much better locality, as you can see from those pictures. It's much better than the usual sync representation. This is not a new invention, but it's just a way to prove things that engineers use already. And of course, if you would do it in 2 dimensions, your repeated spectrogram might look like this. So this might be the original spectrogram, and this might be a lattice in the Fourier domain, which is telling you what kind of sampling lattice you should use. Now, engineers learn that periodic discrete signals are living on a different group in abstract harmonic analysis, but there are also elements of S0 prime. So they have a Fourier transform, and one can show that each periodic discrete signal is a sum of shifted Dirac comps. You have the red Dirac comp, the blue, and so on. They are a weighted finite sum of Dirac comps. And each Dirac comp has a Fourier transform, therefore the linear combination. And if you ask what are the coefficients of these, then you find out that it's exactly the discrete Fourier transform formula or FFT formula. So you can approximate elements from S0 prime or mild distributions by test functions, by smoothing them out, localizing them in one or the other order, or by approximating them by fine samples with a big period. And in this way, you need one result, which I only mentioned to come to an end. If you're thinking that you would like to use the FFT in order to compute the Fourier transform of a function, you would say, I have to sample on a regular lattice fine enough and long enough until more or less, if you have a compactly supported function, you're kind of taking the support. If you take a Gaussian function, maybe you sample from -5 to +5 or so at a sampling rate over 1 over 10 or so. Then you have your period is 10, your sampling rate is 10, and you get 100 samples. But in this way, by showing that for an S0 function, you can recover from these sampling values just by doing a simple, let's say, triangular interpolation. You have a very strong interpretation. You can do the Fourier transform of a general function using this formula. So you're saying, if you're giving me your f, and if I sample fine enough b and I periodize coarse enough a, and the product of n times b should be a, so the sampling parameter should be the period should be a multiple of the sampling parameter, then you can do this abstract Fourier transform using the DFT. And so on the Fourier transform side, you can try to come back to the f hat by choosing all these parameters appropriately. I have no time to go to the kernel theorem, but it's an amazing thing that the kernel theorem, which people know for the Hilbert-Schmidt operators, can be extended to this setting, despite the fact that we are having Banach spaces, which are definitely not nuclear Fauché spaces. So then, nevertheless, we have a kernel theorem. I just want to mention that if you give me an operator with a kernel in S0 of 2D, so this is the inner kernel theorem, you're getting an operator which is mapping S0 prime into S0, even weak star to norm continuous. But the well-known theorem is L2 kernels are Hilbert-Schmidt operators on L2, or you're saying you have S0, the most general operators, as I had for this nasty frame operator for general L2 elements, and that would be something with a kernel in S0 prime of 2 variables. And this is already basically done in my article with Werner Kotzig in the book of 98. But it has gained enough attention now in the last few years and has been used widely. I would like to come to an end and thank you for your attention and ask to ask questions if you have them. Thank you very much.